Global to be producing this amazing series. This is our last session of the spring, which was all about agents. And for the fall, please suggest papers you think we should go through in the chat. We're always welcoming suggestions. We are under Linux Foundation AI and Data, so quite heavily anchored in open source, and we are on a mission to advance human-centered future for AI. And so to produce this session, we've collaborated with Mohammed, who I see has just joined, who is affiliated with Mozilla AI. And so as you can see, it's a hugely collaborative initiative. And so I would love to hand it over to Ali now, who is our amazing speaker for today and the author for Titans Learning to Memorize a Test Time paper, which I think will be really useful because it's actually on the applied side, really quite practical. So excited to get through it today. Ali, over to you. Please introduce yourself and yeah, feel free to dive in.
Thank you very much. I'm so glad to meet you all. And I was wondering whether you can see my slides.
Yeah.
Great. Hello everyone. I'm Ali Behrouz, and I'm a PhD student at Cornell University, and also research intern at Google Research. And I'm going to present our work on Titans Learning to Memorize at Test Time, which is a joint work with Pei-Ling Zhang and Wahab Mirogni. I'm going to start the talk with we generally talking about different perspectives that can help us to design more powerful architectures. The architecture basically in neural networks, and when we think about deep learning architectures, the uh, the way that we put different things together is somehow the way that we are we assume that our brain is like putting different neurons together to do different things. And so initially most of the seminal studies like LSTM were somehow were actually they inspired by memory perspective. They said that memory is a neural update caused by an input, and then the learning process is something, some process that we use for acquiring effective and useful memory. So given this perspective, they wanted to get inspired from human memory. So at that time, basically our understanding was we have something like a long-term memory and short-term memory, and we want to somehow combine these two together. We as human, we forget about things, so basically we want also forget gate. So all these intuitions result in designing, for example, LSTM or similar architectures at that time. So we know that this perspective is very helpful. But after that, there's a transformer and efficiency era. So what we are seeing there is that we focus on efficiency part. We want to take advantage of matrix multiplication as much as we can to take advantage of the accelerators that we have, so make everything faster, and everything is just dominated by transformers. And then starting from 2018 or so, we can see some new perspective about how we can model sequences as dynamical system, how we can see sequences as dynamical system, and then use, for example, different methods in dynamical systems. For example, we can use state space models for linear approximation, and actually we can see that surprisingly they are very effective. Then we have something like we can learn about the state space models have something like a convolutional form in the data independent way. And then, for example, we have discretization. Somehow this discretization process can extend the forget mechanism, and so on and so forth. We can learn different things from this perspective. But if we look at all these things, we can see that there's one mathematical formulation, There is nothing else. It's just one mathematical formulation. But there are different ways that we can somehow interpret that single mathematical formulation. And one thing that I really believe in is that if we just look at the mathematical formulation, it would be really hard to somehow like see what would be the next step. What do we want to do, for example, to improve these architectures? And based on that, I really think that we need to go back to the memory perspective. So this is the era I would call it like modern memory perspective, because we have learned so many things from transformer era and also the dynamical system perspective, and now we can like combine all things that we have learned and also like get inspired from human brain to design more powerful architectures. And I'm going to like discuss more about like this perspective. But before going into the details, let me explain why I think this perspective is really important and can help us to design better architectures. So if we look at our brain, we can see that our brain has evolved for more than millions of years. And so basically, if we just like look at that, we can see that it's very effective and efficient. And so it's like a great source of inspiration. So we can learn from it and see like how we can design better artificial neural architectures. So like given that perspective, I need to again emphasize that learn, if we want to like learn from that perspective, we should say learning is the process of acquiring effective and useful memory. So everything is just compression. We need to see how we can compress the data into a memory, so somehow we learn from the data. And now, another thing that is very important here, I think it's a very important intuition about like designing these kind of architectures, is that we as humans do not have persistent long-term memory, but we do have like we do have persistent long-term memory, but we do not have infinite context. And what does that mean? It means that in our working memory, we doesn't have all the context that we know, but there is another like module which is our long-term memory, and anytime that we need to have access to some information, we can like get access to that and extract some of the useful information. So given this perspective that I mentioned, what are we missing in current architectures? So one of the first thing is that neural network need to constantly memorize and learn. So we do not have something like a pre-training process in human, like in humans, we do not have something like a pre-training process and then post-training process and something like that. It's just humans are constantly learning from the data, from the input. Another thing, as I mentioned, is that we do have persistent long-term memory. We can remember so many things from, for example, 10 years ago, 20 years ago, but we do not have infinite context. We don't have all the details from, for example, 20 years ago. So that's another important part. Another thing is that let's look at our short-term memory. Our short-term memory, which usually corresponds to a memory that stores, for example, the past 20 seconds, 30 seconds, it's a very accurate memory. We do not hallucinate about the information that we just got in, for example, 20 seconds ago. We remember all the details about like everything about like in the past 20 seconds. But if we look at our long-term memory, we can see that we might hallucinate, we might change the details into our mind, we might, for example, forget some parts. And so basically it's a fading memory over time. So it's very similar to how attention and how recurrence model works, because attention is very accurate. It considers all the pairwise interactions between tokens, and on the other hand, we have recurrence models, which use a fading memory, and they need to like properly manage their memory. And finally, the last important part is our memory is not a simple set of neurons, but a neural architecture. So we should not consider a simple set of neuron as for example, our memory and just like compress everything to just one vector or something like that. So let me like elaborate more on that. But to go into the details, let's review how recurrent models work in a very high level. So let's say that we have like this incoming data here, which is a sequence. What we do in like recurrent models is that we have a memory which usually called a hidden state. We project the data into our hidden space. Then we have this memory which is our hidden state. We project the memory as well, and then when these two things are in the same in the same hidden space, then we just add them together and replace it with the memory, the next state of the memory, and we just repeat this process anytime that we have a new data. And at the retrieval process, we just like multiply this memory by a matrix, so the output would be like the result of this multiplication. So that's how generally traditional recurrent models work. So given this perspective, the question is like, are we really making process like fundamental process over time? So we can see that, for example, if we look at RetNet in 2023, the mathematical formulation is like just this one that we have here. And if we look at, for example, in Mamba 2 architecture 2024, we can see that the only change is just like this part. The alpha is now data dependent. So we can see that we are just changing how we do this update process, but we are not changing like the entire process, and we are not making like fundamental changes to the type of architectures that we are using. So uh, basically, um, before going into the next generation of like architectures, let me also discuss how linear transformers work. So linear transformers in the causal setting are also recurrent models. Why? Because if we replace the softmax activation with like a separable kernel, then we can separate these two parts instead of like the multiplication of qtki in the attention. We can just separate these two parts, and then if we do that, then we can like rewrite this process as follows. And if we look at this part, I'm not sure whether you can see my cursor, but generally this summation in the here in the summation in, for example, it says like the kernel of ki transpose times vi. If you look at this part, we can see that this part is somehow acting as the memory of the linear transformer, because it's like storing the connections between ki and vi, or keys and values here. And this summation can simply be written as a like recurrent process. So basically, empty is our uh, memory at the memory state at time t, and then we update the memory state using just by adding a new multiplication of the new pairs that we have. And so basically the linear transformer is also a variant of like recurrent models in the causal setting. So now again, let's go back to the like very high level process for the next generation of architectures, or for example linear transformers. And so basically here again, everything is almost the same. We have this data, we project the inputs into the hidden space. Also, we have this memory, we project the memory, and basically we just add these two and replace the memory, and so on and so forth. The only thing that is changed here is the architecture of the memory. You can see that here we have something like a matrix instead of the vector. And basically this matrix can store more information, and it's more powerful than a single vector. So that's like the next generation of architectures in like recurrent setting. Now we can like extend this idea. We can instead of like we start with a vector, then go to the matrix. Now we can use any neural architectures. And this idea is discussed in like several papers, and I mean even like very old papers. So this part is like something that we are learning from the like literature, because it's really important to somehow like store the data that we have into the parameters of a neural architecture, which we call it neural memory. And so this architecture is going to learn how to memorize the context at test time. But the question is, when we have a vector or when we have a matrix, the process is very simple, because as I mentioned here, we just need to like multiply the memory or project the memory and also project the input, and then just add these two together. That's generally the process, and it's very simple. But when we have a neural memory, what do we want to do? How can we like project this neural memory, or what is the general process for updating the memory and like storing the input data into the parameters of the memory? And the idea is that we just need to like train this neural memory, because when we train the neural memory, it's learning the samples and it's learning how to model inputs data, and so basically it is just memorizing it over time. So that's the main idea here. So given like this process, how do we want to like retrieve some information from the data? And basically the retrieval process is just a single forward pass over the memory. We just pass the data into the memory, and the memory using a forward pass gives us the corresponding information about that query. And so given like these framework that I mentioned, the question is, what should we remember at test time? So, as I mentioned, the memory is a fixed size memory. And so we cannot just store everything into our memory. We need to prioritize some of the events over others. So, what event should we memorize? Again, we take inspiration from the human memory. We say that, we usually memorize things that are surprising to us. So, given this perspective, the question is how we can measure this surprise metric. And so, the idea here is that the simple idea that we can use is to use, for example, the gradient of like one objective that measures how we map keys to values. And based on the inputs data, we take the gradient to see how different this inputs data is from all the data samples that we have stored in the memory mt minus one. So this gradient part measures like the surprisingness of this incoming data, and based on that we can like update the memory. The more surprising the data is, the more affect it has on the memory module. But the main issue with that part is we are just looking at one token at a time without like considering anything in the past. But for example, you might hear a very surprising news that got your attention, and you know after that everything is just like some normal conversation or normal input. And if we just focus on the surprise metric that I mentioned, we might miss the following tokens after a one very surprising token. But if we do that, then we might just miss the context, because the context depends on all the tokens in that specific period of time. And so basically what we do here is that we break the surprise metric into two parts. One is the momentary surprise. It measures how the input data is different from the past like state of the memory. As I mentioned, we do that using the gradient part. And then we have the past surprise, which somehow is the summation of like, not usually the summation, but the uh, somehow compressed surprise version of the past data that we have. So basically, the idea here is that uh, we have this past surprise from the past, and there's a decay mechanism here, which like measure uh, measure how we want to, uh, for example, how do we want to uh, use the past surprise in this momentary surprise, and how do we want to like combine these two together. So that's generally the main idea of how we measure the surprisingness of like inputs data and how we update our memory. But as I mentioned again, it's like the fixed size memory. So even using like this prioritization, we might not need some of the very old information, so we need to somehow forget some of the information that we already learned from the past. So basically, we incorporate something like a forgetting mechanism. So generally, the idea here is that we multiply this memory module using 1 minus alpha t. And if alpha t is close to 1, it means that we just need to raise the memory and just look at the current input. And if it's like close to 0, it means that we should like retain all the past state of the memory. And the context is relevant, so we need what we have learned from the past. So this alpha parameters is learnable and also is input dependent. So based on the data, we decide whether we need the past like state of the memory or not. So the question is like, we have learned that how we can like design this neural memory, but the question is it like fast enough? Can we like parallelize the process? And unfortunately, it's not parallelizable in the current form, because you can see that this empty depends on its past state in two different parts. One is in the gradient part, and one is here, and generally it's not parallelizable. So what is the idea here to train like this architecture? The idea here is that we can replace this gradient part and take the gradient with respect to the last state of the previous subsequence. So let me explain it in another way. Basically, we have a long sequence of data, and the idea here is that we can like split the sequence into some chunks with the same size. And now, given like having each of these chunks, we start with taking the gradient part with respect to the last state of the previous chunk. If we do that, we can calculate all these gradients parts at the same time before starting the process for this specific chunk. And so basically, we can have something like this gradient part is just ut, and ut is the input, and we can see that this process is just a linear recurrence. And if it's linear recurrence, we can just like you know uh, parallelize it using, for example, the scan associative scan algorithms, or for example the matrix multiplication format of these kind of architectures. And so basically, if we do this approximation, then we can provide parallelizable training. However, if we want to somehow take advantage of the accelerators like TPUs or GPUs, we need to like design the process so it use more matrix multiplication. And the interesting part is that this general process can simply be rewritten as the matrix multiplication, because let's just here we have like the recurrence of the memory that we have. And if we just expand this process, mt minus 1 can also be written as the mt minus 2, and so on and so forth. We just need to like expand the recurrence part. And if we do that, then we can see that this part is equivalent to this part, where beta t is just the multiplication of the past 1 minus alpha j. And so in this process, the first term is just like a simple multiplication. So we don't need to be concerned about like this part. And the interesting part is that the second part is also a simple matrix multiplication, because the loss function that we are using is just a like regression loss, L2 regression loss. And so if we take the gradient, we can see that the gradient can be written as this form that we have here. If we just replace this part here, we can see that this summation is equivalent to this matrix multiplication, where this theta B matrix is a diagonal matrix with value like theta I, and this B matrix is the diagonal matrix with value beta I. So again, we can like make the training process very fast using like this matrix multiplication inside each chunk. Now we have learned that how we can design the neural memory, how we can design, how we can like design more efficient algorithms for the training of the neural memory. And now the question is how we can combine like a memory module with like attention, because as I mentioned, attention is very similar to the short-term memory, and then we have the memory like long-term memory, and how we can like combine these two together. So basically the idea that we have here is like we see short-term and long-term memory as an interconnected system that each of them is helping the other one. So basically the data comes, we pass the data into the neural memory to get relevant information from like the past, and then we concatenate the output of the neural memory to the sequence and pass the sequence into the attention. So the attention has the relevant information from the past and also the actual sequence that we have here. So it can decide whether it needs to somehow use the current information or use the historical information from the long-term memory. And the output of the attention will go to the neural memory to update the neural memory. So basically, in the first part, the neural memory is helping the attention, and in the second part, the attention is helping the neural memory part. So that's generally the process. Another variant that we present here is that memory as a gate. So basically, the data comes, we treat long-term and short-term memory as two different branches of memory. So data separately goes to long-term memory and separately goes to the short-term memory. And then the output of these two is going to just like be concatenated, or for example be combined. The output would be just a combination of these two branches of memory. That's another way that we can like combine long-term and short-term memory. Finally, the last variant is memory as a layer, which is very common in the literature. Usually people just combine RNN with attention in a sequential format. So basically the data comes, goes to the neural memory, and then the output goes to the attention. Or you can just like reverse the process, that the sequence goes to the attention and then goes to the neural memory. Depending on your design, you can like use each of these two type of architecture. I don't think that like there's like a huge difference in the performance, but generally for some reasons you want to do that. And so yeah, we learned like how we can design neural architectures, neural memory architectures, how we can like make them faster, and how we can incorporate attention and neural memory. And now we want to see like what is like what is the performance of these models that we discussed. And we can see that like in language modeling and common sense reasoning tasks, Titans without any attention, just the neural memory part, it can outperform all the best baselines, including transformers and also hybrid models. And also, if we add the attention part, we can further improve the performance and gain more like effectiveness. Another task that we have focused on is the Boblong benchmark, which is somehow a needle in haystack style. It's not exactly the same as like needle in haystack, but generally it's like a needle in haystack style state tracking task. And so basically, what we have learned from this experiment is that like Pythons are very effective in long context because they can store, a lot of like information into their parameters, and so they can scale to, for example, 1 million or 2 millions with like good quality. So here I need to emphasize that the architecture matters a lot. The way that we do, for example, this Titans memory as a context is very important to achieving such performance. If we just replace it with, for example, memory as a layer or memory as a gate, the performance can drop. So basically the architectures and the way that we combine memory, long-term memory and like short-term memory matters a lot. And also it's like important to say that, we have some ultra large models as the baseline, like GPT-4o mini, or for example llama models, uh, with using like 70 billion parameters. So basically we just follow the design of the benchmark and fine tune like small models like Mamba, or for example Titan or RMT, and yeah, generally they are fine-tuned model. They are not just like zero shot. It's not their zero shot performance. And finally, we have like this ablation study. So basically, I think one interesting point here is that memory as a layer, as I mentioned, is very common in the literature, is not the best way that we can combine long-term and short-term memory. And also this momentum part, which is somehow the breaking the surprise into the past surprise and momentary surprise, is very important for long context, because we can get much better results in long context when we use momentum. And also this weight decay is actually the forgetting part. Again, we can see that the forgetting part is very important for long context task. And also, like, we can somehow see there is like no free lunch here, because memory as a context performs better in like reasoning and long context, but memory as a gate performs better in the language modeling. So definitely there might be some like more interesting study to see like how we can combine memory as a content. I mean, how we can combine memory and like attention in a hybrid way. And so yeah, that's generally my talk. We are actively like working on these kind of architectures. If you're like interested, please reach out. And also we have like two follow-ups on Pythons. I mean, generally in this direction, and like I think they can help to like get better like intuition about like why these models should work. And like we have also Atlas here, which somehow extend Pythons to like memorize the context instead of memorizing the tokens. Yep. Thank you very much. If there is any question, I would be happy to discuss.
Okay. Yeah, I see quite a few in the chat. So let me pull some out. Okay. Here's a question from Brian Boyd. He's asking, does the neural network remember relationships, or do they get squashed as it happens in vector stores? And can a neural network capture memory better than a knowledge graph or triple?
Uh, yeah, definitely. I mean, definitely one of the things that is like important to, I mean, right now we are using MLP, but definitely, for example, there are different ways that you can store the knowledge that the model is learning. So using, for example, knowledge graph is like very interesting process. I'm somehow skeptical about like the efficiency part if we use something like knowledge graphs, but definitely that would be very interesting to try.
Great. I mean, from my perspective as well, knowledge graphs can be a little bit clunky to work with, so they're slower. But being able to maybe integrate triples within the model somehow sounds really exciting to me. So, because the triples can store relationships, and I think the relationships going relationship to relationship to relationship, there can be real value there. So, uh, awesome paper. I appreciate your work.
Thank you.
Amazing. I am just pinging someone else to see if they want to directly ask the question, which is a great name, Context Found. Okay, I'll ask it then.
There we go.
Oh, there we go. Okay.
I'm allowed to speak. Hey, thank you.
You are.
Thanks for the presentation. It's really interesting and just, yeah, would love to see this bear more fruit on it. Do you have a gut feel for which method of integrating MAC or MAG or MAL, which one you think will actually bear fruit the most going down the road? I see that two of them are showing stronger performance according to the paper.
Yeah, I think, yeah, as I mentioned, I think at least in the experiments that we have seen so far, there is like no free lunch. So none of them is like the best and can like dominate others. The interesting part is that like the memory as a layer somehow like is weaker than the other two in like all the tasks. But the other two are effective in different ways. So I think in general there might be something like uh, you know probably based on the task that we have or the application that we want to use. Probably we can see some like different types of way that we can combine these things together. Because for example, if your task is very like similar to something like language modeling or question answering, then probably uh, memory as a gate would be a better option. Or for example, if your task requires a very long context, then memory as a context might be very useful. So yeah, I cannot like say I mean I don't know that which one is like better in all the cases, but yeah, I think at least based on the experiment that we have, we know that for some tasks, memory as a context is better, and for some tasks, memory as a gate is better.
Is MAL just right out? Is it clearly underperforming the other two?
At least in this scale and the the task that we have, it underperforms the other two, but yeah.
Interesting. So Vladislav, do you want to unmute and jump in with your question?
Sure, yes. Can you hear me?
Yeah.
Yep. Thank you. Thank you, Ali, for the presentation. Very interesting paper. I wanted to ask you about the efficient computation for the memory term that you mentioned that you wanted to optimize for usage with GPUs and TPUs. So if we take the whole matrix X, I would imagine that the problem could become infeasible if the context is too big or the amount of samples is too large. Do you use still batches and then compute the batched memory terms? If so, how do you combine them, or how do you work with large amount of X in these cases?
Yeah, so basically in this like matrix multiplication format that I mentioned, please note that we do this process for each chunk. So basically we have divided the sequence into some small subsequences, and each subsequence, no matter how large the sequence is for example some numbers like 64 or 128 or 16 or 8, depending on the task that you have. And so basically they are not that large. So the dimension of like these, for example, this matrix X here is not that large. It's just the data corresponding to this specific subsequence that we have focused on.
Amazing. So
Yes. Can you hear me?
yeah, you're next.
Thank you. So this is on. Thank you very much for your presentation. We live in an era of agentic system where there are multiple subsystems within within a product, and we've built some solutions where we've got different LLMs working, doing different tasks specialized for different areas. And so could you, kind of give us a pro and con of trying to build this long-term memory into an LLM rather than depending on other databases or subsystems to extract that the relevant data for that particular task.
Yeah, I see like these two line of work somehow orthogonal because each of them can help the other one. I mean, there is like no restriction to use, for example, all those techniques, for example, retrieval augmented generation or RAG, so or other techniques like anything that for example has access to the any databases and all these things, we can apply all of them to Titans as well. So basically, the main comparison is based on Titans vs other like architectures, other linear RNNs, or for example, transformers. When we have a trained like LLM, then you can like use all those techniques, like all the techniques that you mentioned. So somehow I see these two somehow orthogonal. Generally, you can like improve the performance of transformer based model plus those techniques. You can improve the performance of that model using like replacing the transformer with Titans. And also, if you do not use like those techniques, you can add those techniques to improve the performance. So I do not see like these two lines like somehow not related. They're related actually, but I mean, I do not see them as something comparable because both can help the other one in different aspects.
Great. And Kina, I'm unmuting you. Let me know if you have issues.
Hi, can you hear me okay?
Yeah.
Okay, perfect. Yeah, first of all, thank you so much for the presentation. I really liked how you opened up with like kind of going back to the history and starting from the RNN and building up, because I feel like a lot of people have stopped talking about that since the transformer. So appreciate that. And I guess like one of your core idea that you were suggesting was regarding like surprise, right? Like that's and I was just wondering if this is like related to the concept of entropy that we've also like, seen from the other other settings of the ML. So if was that the motivation behind building this kind of idea, or yeah, if you could, just elaborate a little bit more, that'd be appreciated. Thank you.
Sure. That's a great question. So basically, here to measure the surprise, we can use so many different measures for like measuring how different things are. And actually, there are like several connections between taking the gradient and, for example, the minimizing the entropy or something like that. So basically it really depends on how you want to like model the process, and definitely there are like different ways that we can connect all these things together. So basically in the paper that I mentioned here, the It's All Connected paper, we discussed different ways that we can, for example, define the surprise metric. And definitely one of the things that we can do for measuring the surprise is using, for example, entropy, or for example using uh, you know uh, other ways for like measuring how surprising the input data is and how is it's different from the past data. For example, we discuss KL divergence in the It's All Connected paper, which can be somehow similar. And yeah, I'm not sure whether it answers your question.
Yeah. Thank you. Josh?
Hi, hey Ali, thank you. This is a great paper.
Mm.
So one of the question I have is that is there a way to like a quote unquote inject memories from text like tokens into the Titan's latent space? Because if I understand correctly, Titan, the memories you're referring to in this Titan paper is all happening in the latent space, right? So can I like inject the tokens from basically outside, somehow transform it into, and then be able to inject it into the memory that Titan uses?
Yeah, definitely. For example, this input data that we have here is just a set of tokens. So basically, when you have some set of tokens, you can just pass them into Titans and update the memory state using, for example, the formulation that we have based on surprise, and update the weights. So basically, in that sense, we are injecting these tokens into the memory.
But that has to like go through a multiple layers, and I guess it's kind of going through its own computation that's happening inside of Titan, right? So what I'm kind of thinking is that hey, I have some other questionnaire that kind of touched on it is that hey, I have like a certain explicit memory saying like my organization policy or something is stored in like let's say the external database or external data graph, and then I want to say hey, use this as some kind of higher priority, and this is my memory while you're computing. So that's I guess like some kind of like a prioritize the memory, I guess. Does that make sense?
Yeah, I understand. So let me just like before discussing that part, let me
Mm-hmm.
emphasize on one point here that like updating this memory, because the memory module that we are using here is just a two-layer MLP, and
Yep.
most of the time it doesn't have that much parameters. So basically, updating this neural memory is like very fast.
Mm.
So it's not time consuming at all. I mean, given the data, it's very fast to update the neural memory and like compress the data into its parameters. That's generally one point. But if I want to be honest,
Mm-hmm.
in the current format of memory, I do not see a clear way to like inject the tokens into the parameters of the memory, like without like going through the process of like surprise metric and so on and so forth.
And the surprise metric was, sorry, I
I
think I
mean, the
got lost on
updating the memory, I mean, the training phase of the memory, passing the data into the memory.
Gotcha. So if I summarize, if I understand correctly, I think during the test time or inference time, if I'm like trying to inject um, certain like a memory that I want to prioritize, which is kind of out of context with the training data. So it'll be a little bit harder to use that during the inference time. I think that's what you're saying.
Yes.
Got it. Okay. Thank you.
Great. David, do you want to go next?
Sure. Hello, great paper. Memory is such an important topic. My question is, do you have any thoughts on moderating the learned memory function in the meta model outside of the suggested superparameters in your paper? And basically, I'm thinking about if I'm dealing with images versus text or other modalities, do you have any thoughts on how that memory would be shaped up?
Uh, Honestly, that's a very interesting question, but unfortunately, uh, we didn't like we didn't do some experiments on that part. I think generally it should be possible to do it. But yeah, I do not have a very like concrete answer to that. But that's a very interesting question, and it's very interesting to see like what would happen.
Yeah, thanks.
Sorry.
No problem. You can't have thought of everything. So, how do you manage information persistence and retrieval across multi-million token contexts?
Do you mean this part, this persistent memory part?
Yeah, this is just about scaling of traditional attention mechanisms. Because if
So
you are to achieve both scalability and accuracy,
I'm not sure whether I understand the question. So basically, the question is about like the MLP layers, or it's about like this learnable persistent memory.
it's more about how you remember and use information from very long contexts without it slowing down like regular attention does.
I see. So basically, there are like two different ways that we can use attention. One is like a global attention that usually people use. Another one is like local, for example, sliding window attention, or for example, segment-based attention. So generally, the global attention is very slow, because if we put all the context into the global attention, then the quadratic cost would be huge for long context. And if we look at the like Mac architecture, we can see that what we are doing is to like use a segment attention. So this segment attention somehow help the model to have better efficiency, because we only attend to the current context. And then the asset from the past memory comes and then concatenated to the current context. It's not too much tokens. So basically it doesn't like affect the context links that much. So if we want to compare that with, for example, global attention, we can see that these additional tokens that we have concatenated to the sequence comes from memory, which is much faster from transformers in long context. So generally, even using Mac architecture, if we want to like train the model and measure the efficiency, we can see that this Mac can be very fast in longer contexts. For like smaller context lengths, there are some like limitations. And actually we can see that transformers, because it's like 8 years or 9 years that we are optimizing transformers, and there are definitely very great implementation for them, but right now, like, at least it's not a very like well optimized process for all of the recurrence models. So generally, it's fair to say that for some context lengths, it's like transformers is faster. But we have also a figure in the paper to show that if you increase the context lengths, I think as far as I remember, after like 8K, we can see that, for example, neural memory or Mac architecture is faster than transformers.
Great. Jonathan, do you want to ask your question next?
Sure. Thank you again for your presentation. It's spectacular. My question is maybe a more mundane one, but given the state of memory today, do you think that these features are causing more harm than good? It's already being touted as a core function of things like Microsoft Copilot, having shared memory, or even some startups that are tackling this place like Memo, which I put in the chat.
Yeah, I think basically one thing that we need to emphasize here is that this memory module uh, is learning how to memorize, which means that at test time, it only memorizes the context that is given to the memory. When the context is done, the memory is done. So we don't use, we just like raise all the memory. So in general, we have not done so many things about like the privacy or something like that. But generally, these models are meta-learned models. They are not learning the training data, but they are learning from training data how to memorize at test time. So potentially, there might be less concerns about like this privacy issue, because as I mentioned, the memory only works in each context. When context is done, the memory is erased, and so like there is no problem, similar to the issue you mentioned. For example, there is no shared memory across, for example, different contexts or something like that.
Yeah, I guess I wasn't framing it from the privacy issue, more of when you're doing like prompt augmentation, there's issues with maintaining context, but then also the concepts of just like how to maintain memory over time and how do you prioritize memory. But good points overall. Thank you.
Thank you.
Great. We're about to wrap up, but I have to ask. Ilyas Sutskever just gave a talk at University of Toronto recently, and called the brain a biological computer, basically saying that it's a digital brain. Any comment on that in the context of memory?
Yeah, I think, everyone, when been working on deep learning architectures or generally LLMs, is just trying to see how we can model the brain in an artificial manner. And, any architectures that we are designing is just some way that we think we can use like artificial neural architectures to somehow mimic the learning process of our brain. And memory is definitely one of those parts, and actually, memory plays a huge role in our learning process. We cannot properly learn if we do not have a long-term memory, if we cannot pass the data or like the information that we got from short-term to long-term memory. So that's a very important process, and that generally it makes sense to call like these things biological brain, but it's different. I mean, everyone has their own like perspective that how we can do that. Definitely, people have different opinions about like whether what we are doing is similar to brain or not.
Great. All right. I think we're at time. Thank you so much, everyone, for joining. This is our last session for the Paper Club this spring. We'll be back in the fall. And so, Ali, thank you personally for taking your time and presenting. Thanks, everyone, for your questions. And please, all of you, you're welcome to suggest papers for us to go through in the fall, and even topics, because we did agents as a macro theme for spring, and we went through all kinds of really interesting conversations. For the fall, please give us a sense of what you think might be interesting to look at and do this and go through this together. And yeah, please keep in touch. I am just going to drop a quick link to my LinkedIn if people want to say hi there. You can also subscribe to the mailing list on the Paper Club's page. I'll drop that in the chat as well. And that way you'll be notified when we create new events for the Paper Club, which will be in the fall. And thank you, Mohammed, if you're still here, for collaborating on programming this amazing edition for the Paper Club for the spring. Without you, I don't know how we would manage. And so thank you so much to AI Thinkers Global as well for platforming these important discussions, because I really don't know if we hear from researchers enough. And so this bridge means so much for us to be building with future roadmaps as opposed to yesterday roadmaps when it comes to applied work and product. Really important to see what the trends look like for people to think